Good evening. It's December 26. Merry Christmas to everybody. This is Professor David J. De Los Reyes. For tonight, I will be having a long video on my subject matter, differential equation. Okay, the topic for tonight will be lesson number 40 on my topic, differential equation. This is DE number 40. I got a numbering on my lessons. So this is now lesson differential equation, lesson number 40. The title of DE 40 is actually second order differential equation. This should now be example number 4. For example number 4, it's another variation, okay? This will be, the roots are complex numbers. So actually, example number 1, those are the real and unequal. Example number 2, those are real and equal. And for this example number 4 now, the resulting roots of the characteristic equation of the second order differential equation are complex numbers. Complex numbers meaning it got a real part and it got an imaginary part. Imaginary part designated by letter I. Okay. So if you are having a roots in which there is a real part and an imaginary part, those roots are actually complex numbers, and that falls under, this should be case number 3. Case number 3 under second order differential equation. Okay, let's proceed for tonight. The given problem is d square y over dx squared plus 2 dy dx plus 6y equal to 0. The problem is asking for GS, meaning the general solution. Okay, let's try to bring out the solution. As always, the initial, what do you call this, the start of the solution is, there is a substitution, that is, we will let y equal to k e raised to mx. That is always the start of the solution. We need dy dx, right? So we will take the derivative of this. Dy dx will be k times e to the mx times m times 1. Constant and exponential function, it should be that constant times the derivative of that exponential function. Okay, which is actually k e to the mx. The exponent is actually constant m in x, so it should be m times the derivative of x with respect to itself, which is 1. So dy dx will be km e to the mx. Same as from the previous example. I'm just showing you the complete, what I call this solution. D square y over dx square is equal to the derivative with respect to x of dy dx. dy dx is km e to the mx. So to bring out d square y over dx square, we will take again the derivative of the first derivative. Okay? And the derivative of the first derivative is m is constant, k is constant, the product of two constant will still be constant. Okay? We bring it out, then it will become the differential of a constant km times an exponential function e to the mx. So it should be km times e to the mx times the differential of the exponent, which is m times 1. Simplifying this, d square y over dx square is equal to km square e raised to mx. I will check my cover. Okay. So we are now through with the computation of dy dx and d square y over dx square with the given y equal to k e to the mx. So we will take this value here and this second value here and this third value, we place it on the given second order differential equation. So substituting, the second derivative is actually km square e to the mx plus 2, the coefficient is 2, times dy dx. dy dx is the product of km e to the mx. The third part is 6 times y. This is 6 times the value y, which is k e to the mx, equal to 0. To simplify the resulting equation, because it seems it's a little bit complicated. No, it's not complicated. There are so many terms and we could eliminate those common terms. And the common terms are actually k e to the mx, k e to the mx, k e to the mx. So to remove that value there, we will take the reciprocal, and the reciprocal of k e to the mx is actually 1 over k e to the mx. That's the reciprocal. So if we try to expand this one, we will multiply all the terms by one of these. This k here will disappear, e to the mx will disappear, this k here will disappear, e to the mx will disappear, this k will disappear, e to the mx will disappear after the multiplication of 1 over k e to the mx. So what comes out on the left hand side will just be simply m squared 2 times m is 2m, 6 times 1 is actually 6, equal to the right hand side, 0 times 1 over this reciprocal is 0. Anything multiplied by 0 will be 0. So this is 0. And the resulting quadratic equation, we term that under second order differential equation as the so-called characteristic equation. Okay? So to solve the resulting general solution, we must have to compute for the possible values of m given the characteristic equation, okay, resulting from the substitution of y, dy dx, and d square y over dx square to this original second order differential equation. So I place it here. To solve for m, I think we could not factor out this by inspection, because the possible factors of m are, or m square rather, the possible factors of m are m and m, right? And the possible prime factors of 6 is actually 3 and 2, right? The middle term is 2m, so we will make the bigger coefficient to be plus. So if this is plus, okay, but this is plus 6, so this could not be negative, so this should be plus also, right? So if we try to check the value of the middle term, this is 3m, and this one is 2m. 3m plus 2m is actually equal to 5m, and this 5m is not equivalent to this 2m here. So this is not factorable by inspection. So the solution of, or the solution for m using factoring is not feasible. Okay, so I will remove this one. So it's a must that we solve the value of m using the quadratic equation, because the characteristic equation is actually a quadratic equation. And if we try to recall the general equation under the quadratic equation, I place it here. This equation here is similar to this form here. Ex squared plus bx plus c equal to 0. This is the general quadratic equation, okay? And we know the value of this by using the quadratic equation, but we must have to specify the value of a, the value of b, and the value of c. And here, for this to be similar, we will put x to be equal to m. So we will replace this by m. Okay? This is m also. And here, we could say that the value of A is 1, the value of B is actually 2, and the value of C is equal to 6. So using the quadratic formula, this is the quadratic formula. This was derived already under algebra using the so-called completing squares. It was derived, okay? That is, the value of any quadratic equation, if we try to compute for the roots, it will be equal to negative b plus or minus the square root. This is not 6 root, guys. We got no number here. If it's only a radical sign like that, it should be square root, not 6 root, okay? This should be the square root of b squared minus 4ac all over 2a. We know the value of ABC already, so it's just a matter of substitution. So this is negative open quantity 2 plus or minus the square root of b squared is 2 squared minus 4 times 1 times 6 all over 2 times 1. Okay, let's try to simplify the 1 inside the radical. 2 squared is 4, and 4 times 1 times 6 is actually 24. Minus 24 plus 4 is actually minus 20. So as you notice it, the sign of the overall number inside is actually a negative sign. And for those who are not, if you are only under algebra, you could not solve this one. But if you are under higher mathematics, we could actually take the square root of a negative number, because we will introduce the value I square equal to minus 1. The imaginary part. We will replace this, this minus 20 can be written as, okay, I will write it here. Minus 20 can be written as minus 1 times 20, right? Then we will replace minus 1 by I square. Imaginary square. And 20 can be written as 2 square. This is times 5, right? Okay? So if we try to take the square root of this is a perfect square, 2 is a perfect square, so they will go out. So that will be plus or minus 2i. 5, unluckily, is not a perfect square, so this is a square root of 5. So actually, don't be afraid if there is a negative sign inside the radical, because we could take the value of that by representing the negative thing as I square. We will replace minus 1 by I square. So what comes out is minus 2 plus or minus. This is minus 1, 4 times 5. This is minus 2 plus or minus. I place it here. I repeat the one I wrote here. See, this is I square, 2 square, times 5 over 2. This is under one radical sign. I square is a perfect square. 2 square is a perfect square. So it comes out already. Okay? That's the value. 2i actually. Yeah. So if the resulting value of m is this. This is 2, this 2 here, this 2 here. So this cancels out. So all will become 1. So what comes out will be negative 1 plus or minus I, the square root of 5. Okay? It is an imaginary number. This is the real part, the first one, real. And the one with the I is actually the imaginary part. Okay? So m1 is actually, by using the positive sign, it should be negative 1 plus I, the square root of 5. m2, by using the negative sign, it will be negative 1, negative I, the square root of 5. So as you can see it, the resulting values at m1 and m2 comprises of a real part and imaginary part. And if there is real part in imaginary part, that is termed to as complex numbers. Okay, then we could specify that the value of alpha is negative 1, the real part. The value of beta equal to the square root of 5, the imaginary part. So this falls under the general solution of second order differential equation under case number 3. That is y is equal to a raised to alpha x times the quantity K1 cosine of beta x plus K2 sine of beta x. It is just a matter of substitution now. Okay? We now know alpha and beta. It's just a matter of substitution. So by following this should be a raised to alpha. What is alpha? Minus 1 open quantity times x times K1 cosine of the square root of pi x. Well, what is the square root of pi? That is beta. Okay? Plus K2 sine of the square root of pi times x. Minus 1 times x is minus x. So as a final simplification, y now, the resulting general solution will be e to the negative x times the quantity K1 cosine of the square root of 5x plus K2 sine of the square root of 5x. That's our final answer. And that is termed to as the general solution. Why general solution? Because for the meantime, we do not know the value of K1 and K2, and since we do not know it, the resulting answer is actually a general solution. It's not a particular solution. Oh, that's it, guys. That is an example problem of a second order differential equation in which the resulting roots of the resulting general solution are complex numbers. It falls under case number 3. Case number 3. Okay? A to the alpha x times the quantity K1 cosine of beta x plus K2 sine of beta x. Oh, that's it, guys. So for those who are taking up differential equation, these are for you guys, okay? So if you like my long video, okay, please click like. If you want to subscribe because you like it, please click subscribe. And if you are generous enough, you can share it to your friends. So you can share to your friends. This is a long video, DE number 40, second order differential equation, example number 4, in which the rows are complex numbers. This is the complete solution if the resulting rows are complex numbers. And by the way, what will be the application of this? I think the application of this is something like in the so-called generation of electricity. Because if we try to graph this one, it comprises of a cosine function and sine function plus an exponential thing. So actually, this exponential thing is actually like a decaying value, and this cosine and sine, it could be a graph of a complicated curve. But we haven't gone to that example yet. I am just presenting what will be the significance of this general solution under case number 3. I think it falls under the graph of a complicated alternating current or alternating current. Okay, that's it, guys. December 26, good evening, Los Angeles.